All right, so we're in the middle of the second to last week, which is really exciting. Goal is to get through some graphs, but tomorrow we're going to have our last exam prep, and Friday we have our last exam in here. So I will get through graphs probably over the course of hopefully 2 days, since we're not doing too much implementation. So my guess is it's going to be today and Monday, and then maybe some of Tuesday, and then Tuesday, Wednesday, Thursday, Friday of next week, we will be talking about interviewing, internships, and job preparation. What can you be doing now to prepare for that? What do you need to be thinking about in terms of preparing for interviews? How do you conduct a computer science interview? Something that I find a lot of graduates are not remotely prepared for. So I have lots of content telling you about my experiences as well as what I would recommend, given who I know in the industry and what they're looking for, and what books have to say on the matter, combining all that into some suggestions. So as a reminder, because tomorrow is an important exam review day, please come with any questions you have to fill up that time. I would like that to be as useful as possible to everyone ahead of one last exam. Any questions about the schedule? I did reveal that binary search tree assignment. I set that to be due a week from Friday. That is the same day that the graphs assignment will be due when I reveal that. Remember that that one is optional and will replace your lowest assignment score if you opt into doing it. All right, we're gonna hit up graphs. Incredibly important data structure. I would argue this is probably, I don't know, they're more challenging than anything that we've seen so far, but also they are quite possibly the most widely used data structure for the most complicated problems. They are kind of a one size fits almost everything. You can structure almost everything as a graph. A tree is a graph with additional restrictions. So graphs can represent really any relationship among any set of items. It's truly powerful. So because of this, we have to talk about the different forms that graphs have, and of course, all of the terms that we use when we discuss graphs. If you're thinking of graphs as an X and a Y and plotting, that is the wrong kind of graph. That is a math graph. I guess it's a way to visualize functions and not a way to concern yourself with a computer science graph. So what is a graph? First of all, who knows the computer science graphs? Who knows what I'm talking about? A couple people, exciting. So all we care about is we have a set of vertices and a set of edges. That tuple of those two sets is the definition of a graph. So what are the vertices? What are the edges? Basically, what's the data that's being stored? And what are the connections between that data? How are those data related to each other? A vertex is just kind of like how we had a tree node. A vertex is a graph node. Just like a tree node, it has a value that we're going to store. And now B in that tuple is just a set of vertices. An edge is just a connection between two vertices. So a tuple tells you the outgoing edge and the incoming edge if it is a directed edge, but there are both directed edges and undirected edges in graphs. An undirected graph just says edges are undirected connections. If you are friends on Facebook, that's not really a directional relationship. You both agree that you are friends with each other, therefore you are friends with each other. There's no outgoing component and ingoing components to that relationship. A directed graph, often shortened to digraph, The edges actually have a source and a destination representing some kind of connection. So a flight from Spokane to Seattle has a direction to it. The outgoing edge would be at the vertex Spokane, and the incoming edge would be at the vertex Seattle, defining the edge between Spokane and Seattle. Just because vertices are involved in the graph does not mean they have to have associated edges connecting them. So some vertices will have some connections, some vertices will not have some connections, and that's okay. Questions on a very basic overview definition of a graph before we dive into the details? Let's look at some examples. Let's define some vertices and edges. You go to a web page and there are some links on those web pages. What are the vertices? What are the edges?
Vertices, the web page, and the links are the edges.
Yeah, yeah. When you click on a link, you go from one website to another website. So the website is a vertex. It exists at some IP address, another website at some other IP address. If there's a link from one to the other, when you click the link on that, you will leave this site and arrive at that site. Yes, I love that game. How about Facebook friends? What are the vertices and what are the edges? What do we think? Facebook friends, vertices, edges? A vertex would be a Facebook profile. And an edge would be some other profile that you're friends with. So the edge between two profiles that says that these two profiles are friends with each other. How about the Kevin Bacon game? Is anyone familiar with the Kevin Bacon game? This is go to a random Wikipedia page. What is the shortest possible number of links that you need to click in order to arrive at Kevin Bacon's page? You can generalize this and say, I'm going to go to a random page and I'm going to go to another random page. And now I need to navigate from this first page to this second page using only links within each Wikipedia page. It's a pretty fun game to play.
Is it?
I think so. It's actually
Right now, I'm not seeing it.
It's a challenge. It is certainly a challenge, but it's a good strategic game. How about programs and methods? Yeah.
Would the edge be the call itself?
Yeah, a method that calls another method. So there'd be an edge between the calling method and the callee, and then an edge back for a return, maybe. So yeah, your vertices would be your methods and your edges would be your method calls. How about roadmaps?
Vertices, cities, and then edges, roads.
Yeah. Cities and roads connecting cities. Airline routes. I already revealed family trees, but airline routes would just be the airports and associated flights that move between those airports. And then family trees, you would have people and you would have relationships between people. Course prerequisites. You have courses and you have other courses that have a prerequisite of that course. So there are edges between a prerequisite course and a course for which that course is a prerequisite. So as you can see, they really can represent just about anything in terms of information and relations between that information. So graphs are incredibly powerful for that reason. We're going to dive into and analyze some undirected graphs to start. So in an undirected graph, edges are two-way. There is no such thing as a directional edge or a one-way edge. Everything, if you can get from A to B via an edge, you can also get from B to A with no further definition. So in terms of logic, you would just say if there's an edge between U and B in our list of edges, that implies that there is an edge between B and U. For those of you in discrete, you're saying, finally, we're using this for something. So only one edge is actually in the set of edges. We don't, if we're storing that set of edges, we're not going to store both UV and VU in that set of edges. We're only going to store one, and the other one is there implicitly. So if UV exists, then VU exists. If VU exists, then UV exists. We can, for a particular vertex, define its degree. That's how many vertices are adjacent to it, how many edges are there. So what is the degree of A in this graph? 2. There are 2 edges that go from A to some other node, B and C. Whereas C has degree 3 and D has degree 1. That's a basic overview of undirected graphs. There should be no arrows on your edges. For digraphs, edges have directions. So there's no implication that if UV is in your set of edges, that VU is in your set of edges. If that is true, then you need to have both of those tuples in your set of edges. If you have, so for instance, there are flights between Spokane and Seattle and Spokane. So you need to draw 2 edges between those 2 vertices, one with directionality from Spokane to Seattle and one with directionality from Seattle to Spokane. In this tuple, we have the source on the left-hand side and the destination on the right-hand side. There's also this concept called in degree, the number of inbound edges for a particular vertex. And then an out degree is the number of edges that are outbound from this vertex. So it's very similar to the concept of degree from the undirected graph, except now we actually split up those arrows that are leaving this vertex and those arrows that are arriving at this vertex. So we'll again use an example. What is the in degree of A? Yeah, 1. What's the out degree of C? 2. What's the in degree of C? 0. Perfect. Any questions on undirected or directed graphs? Right. So we can have self edges if a vertex has an edge to itself. That is certainly possible in some situations. So an edge that is from one vertex to that vertex is a self edge or a loop edge. Those would be the 2 ways to describe that concept. However, there are many graph types that actually disallow this concept or limit the number of them in the entire graph, and also many that don't care how many of them there are. So really depends on the situation. More terms. A connected graph, every vertex in the graph can be reached from every other vertex. We use, this is again borrowed from discrete. This just refers to the cardinality of a set, right? If you've seen this before, so this is the cardinality of V, which is also the number of vertices in the graph. Same thing for edges, cardinality of E, since we're listing both of these as sets, we use set notation to describe them. So the size of E, the cardinality of E, is the number of edges in the graph. What's the minimum number of each? In terms of each other. So is there a minimum number of vertices in a graph? Not really. But what about the minimum number of edges in a graph compared to the number of vertices in the graph? Is there a minimum number of edges?
Is it less than the number of vertices?
If we wanted a connected graph. A connected, undirected graph. But as we saw on the first slide, vertices can stand alone with no connections whatsoever. So the minimum number of edges in a graph is actually 0. It gets more interesting when we can talk about the maximum of each. How about the maximum number of vertices in a graph? Also kind of a boring question. There is no maximum to the number of vertices in a graph. However, there are a maximum number of edges. What is that maximum number of edges compared to the number of vertices? If we only allow one incoming edge and one outgoing edge, both for a, let's talk about this in terms of an undirected graph and a directed graph. So an undirected graph can only have one connection between two vertices, and a directed graph can have two connections between two vertices. What is that maximum? D minus 1 total edges? I don't know if I belong. I don't know if I buy that. Let's draw it out, see if we can come up with the pattern from logic. I have for undirected. If I have one vertex, what is the maximum number of edges? 0. If I have 2, how many? Maximum number of edges between two vertices in an undirected graph. 1? Yeah, you connect them. We now have 3 vertices, maximum number of edges. We have 4 vertices. How many can be between them? 1, 2, 3, 4, 5, 6. Do we see the pattern yet? Here it is again. How many times have we seen this quarter? This actually is apparent logically, because let's say we add a 5th vertex to this. It's the same subgraph, but now we have to connect this to every existing 1, 2, 3, 4 more. So this plus 4 would give us 10. Add another one, we have to connect it to every existing one, plus 5. Add another one, plus 6. Add another one, plus 7. So it makes intuitive sense, but it's yet another 1 plus 2 plus 3 plus 4 plus 5 problem in terms of the number of edges. So based on the number of vertices, it's the number of vertices times the number of vertices plus 1 over 2. Or the number of vertices squared plus the number of vertices for 2. How about in a directed universe?
It's twice that.
It is just twice that. 2 times 0 is 0. 2 times 1, we now have an outgoing and an ingoing to each one. Here we have outgoing and ingoing for each one. We're going to take each undirected vertex and split it up into an incoming and outgoing edge. So, yeah, and the directed, it is twice as many. More definitions. If we have the edge UV in our graph, then we call V a neighbor of U. And of course, directionality matters. So in a directed graph, if an edge points one direction, then the neighbor only flows in the direction of the edge. Questions on anything we've talked about so far? Yeah. Yeah, so if we look back at our outbound and inbound edges, so for a particular vertex, we just care about, okay, how many edges are pointing away from A that originate in A and point at something else. So those are the outbound edges, for the out degree. The in degree is how many edges are coming inbound, have an arrow that originates somewhere else and then point into that vertex. That make sense? Any further clarifications? All right. Edges can have weights, which means that these edges are not necessarily the same length or the same distance. We can have associated costs or weights with those edges. Some graphs allow for negative weights, but many actually do not, because it breaks a number of the algorithms that we use to analyze graphs if there can be negative weights. Of course, in some situations, we need to model something with a negative weight, but usually it means we need a more complicated algorithm to deal with that. So as an example, let's just take some Western Washington ferry routes in terms of the number of minutes that it takes to go from one to another. So that's the length of the ferry rides in Western Washington. So we can see that it makes sense to actually put a weight on those edges. How many minutes do you expect between when the ferry leaves its source and when it arrives at its destination? We don't just want to think that all of these ferry routes are equivalent to each other. They're not necessarily. There's additional information that we might want to put in this graph. Oh, my hometown's on there. Where's one? Edmonds. So we can also talk about paths. We can say a path exists from some vertex to another vertex if there is a list of intermediate vertices such that there are edges between each of those vertices, between the source and the destination. The source of that path and the destination of that path. So we start at one location and we see if we can traverse the graph in any set of the edges in the graph to arrive at the destination. If there is a path that starts and ends at the same node, then we call that a cycle. So let's take a look at a graph. This graph that I don't reveal at the right time. That is bad. Let's very quickly switch the animation. All right. For this graph, go ahead and write 3 different paths and then 2 paths that are cycles. So what's an example of one path in this graph? Lots of options to choose from. Yeah? Via what? There are lots of different paths from Seattle to Dallas, but to identify a particular path, we have to go through and define the list of intermediate vertices. So, yeah, through Salt Lake City. Seattle to Salt Lake City to Dallas is one path. What's another one? Yeah?
Seattle, Salt Lake City to Chicago.
Yeah, Seattle, Salt Lake City to Chicago. Another one could be Seattle to San Francisco. It does not have to be long. A path can be just to your neighbor. How about paths that are cycles? What's a path that's a cycle in this graph? Yeah,
Is it a cycle if it goes directly to a neighbor and back, or does it need?
can be. Yeah, it's undirected. So Seattle to Salt Lake City to Seattle is a cycle.
But then also Seattle, San Francisco, Salt Lake City, Seattle. So
Exactly. Yep. In Seattle to San Francisco to Dallas to Salt Lake City to Chicago to Seattle is a cycle. Seattle to Chicago to Salt Lake City to Dallas to Chicago to Salt Lake City to Dallas to San Francisco to Salt Lake City to Seattle is a cycle that has cycles inside of it. It gets arbitrarily complicated. So we can talk about the path length. It's just the number of edges in that path. So 0 edges if you're going to yourself. 1 edge if you're going to a neighbor. The path cost is just the sum of all of the weights of the edges. If it's an undirected graph, they don't have weights, so it's just the number of edges. But in a weighted graph, then we actually have to calculate that cost. So let's look at the number of hours of a flight between these associated cities. We could say the length of a particular flight. Maybe we are going on a tour of part of the US and we go from Seattle to San Francisco to Dallas to Chicago to Salt Lake City to Seattle. The length of that is 5 because there are 5 legs to that flight. To that set of flights. And then the cost would just be the sum of all of the edge weights. So the cost of Seattle to San Francisco is 2, number of hours. Cost of San Francisco to Dallas, the weight is 3. You wait 3 hours to get there. From Dallas, 2.5 hours to Chicago. From Chicago, 2 hours to Salt Lake City. From Salt Lake City, 2 hours to Seattle. But wait, there's more. I'm just on a roll. That's what's going on. A simple path is one that repeats no vertices. The first can be the last. We can redefine cycle now as a path that ends where it begins. But there's also the concept of a simple cycle, which is a cycle that is also a simple path, repeating no vertices. So that cycle on the last slide was a simple cycle. We went from Seattle to Seattle, but we never visited the same city twice, except for our source and destination. Seattle was where we left. Seattle is where we returned to. Great. On the other hand, if we'd gone from Seattle to San Francisco to Salt Lake City to Dallas to Chicago to Salt Lake City to Seattle, that is not a simple cycle because we visited Salt Lake City multiple times. We can also now define a complete graph, which says for every pair of vertices in the graph, there is an edge between those vertices. So here's an example of a complete graph. There is no pair of vertices that does not have an edge between them. In order for a directed graph to be a complete graph, there must be incoming and outgoing edges to every vertex from every vertex. To be strongly connected, that's that concept of complete or directed graphs. We're going to call that strongly connected. Well, not quite, because so there's a path from every vertex to every other vertex. So here is a strongly connected directed graph, because we can get from every vertex to every other vertex via some path. For a directed graph, a weakly connected graph says that there is a way to get from each vertex to every other vertex if we ignore the directionality of the arrow. So here's an example of a weakly connected graph. We can't get from every vertex to every other vertex, but if we turned it into an undirected graph, we could. Questions on any of this? Kind of a big information dump to start the start. We will have something that's a little bit more involved and engaged here in a bit. Let's start making connections between the tree objects that we talked about and a graph. So how are trees and graphs related to each other? So a tree is a graph with the following conditions. It must be undirected. It must be acyclic. And it must be connected. So this is not quite the same as the trees that we have studied because there was directionality between parent and child. But to be a tree in the most abstract definition of a tree, we do not need that connection. So all trees are graphs, but not all graphs are trees. Here is a tree. This is a graph that is also a tree. So first of all, the edges are undirected. It is acyclic, which means that no cycle exists in this graph. We can't get from a vertex to that same vertex via a path that doesn't involve reusing an edge. And it is also connected. There are no vertices that don't have an edge to some other vertex. There's a way to get from every vertex to every other vertex. Is the real way to think of it. So this tree becomes more interesting when we make it a rooted tree, because that tree did not have a root associated with it. So the trees that we've studied throughout this quarter have all been rooted trees, which means that we identify one of the nodes in the tree as the root. Once we make a rooted tree, we can add directionality to the edges that say, starting at the root, every edge that connects the root to some other vertex is an outgoing edge to the root. Nothing goes into the root. So once we choose a root, it makes a unique rooted tree. So we can see that when we select A as the root of the graph on the prior slide, we get a unique directed tree. You just kind of swing everything over and it looks like the tree that we've seen. On the other hand, if we choose F as the root, you get a very different looking tree. Same graph, different tree. Questions on rooting trees and how trees are formed out of graphs? Yeah.
So because the directionality means two that you draw as trees, they're connected, but you can.
Yeah. Yeah. Let's, yeah, question.
You don't have a root for just a normal tree graph, how do you get access to it?
You wouldn't store it as the object that we wrote. So there is, if we don't define a tree, or sorry, if we don't define a root, then there is no root. there's no place to start. It's still a graph. That graph could become a tree if we selected a root, basically, but we call it a tree because as soon as we pick a root, now it's a directed tree. Now it's a rooted tree, and now we can start doing something interesting with it. So whether it's possible to do that or not is the most abstract definition of tree that we can come up with. Great question. Anything else? All right, let's talk about the density of a graph. So we know the number of edges on a graph is between 0 and the number of vertices squared. So if we have the number of edges in big theta of the number of vertices squared, we're going to call that graph dense. Or unofficially, the graph has lots of edges. Gotta love that unofficial terminology. So if we can define that as this graph grows in size, the number of edges stay proportional to the number of vertices squared. That means that for each vertex, there are a number of associated edges that grows based on the number of vertices in the graph, not 1 or 2. If each vertex has 1 edge or 2 edges, then it's in more big theta of b and not big theta of b squared. But if each vertex has a number of edges, the number of vertices minus some constant, or it's based on the number of vertices, then you end up with something that is quadratic. On the other hand, if it's linear, the number of edges are proportional to the number of vertices directly, then we call the graph sparse. Or most of the possible edges that could be in a complete graph with these vertices are not there. This ends up being a very important distinction when it comes down to what structures do we want to use to store the edges, the connections in the graph. Because we want to be able to answer some questions about a graph reasonably efficiently. So storing a graph doesn't really work well by itself. We need some way to store the edges. We can store the vertices and we could store all of the neighbors to those. But if we wanted to answer questions like, is there an edge between one particular vertex and another particular vertex? Where do we start? With a tree, we started at the root. With a graph, we have to just search the graph, starting at an arbitrary location and waiting until we go find that node. So we often, with graphs, store an additional structure that represents the internal representation of the graph. If we store something with it, then we can answer queries about it faster. So let's talk about that. We really have 2 options for storing a graph in code. Rather than making just a bunch of nodes and edges, we're going to either store an adjacency matrix, which is just a 2D array or a 2D list. Or there is an adjacency list. And we're going to talk about each of these in turn. So let's start with the adjacency matrix. So you're going to instantiate a number of vertices by number of vertices 2D array of Booleans, true false values. A particular cell in that 2-dimensional array is going to be, is there a connection between the row vertex and the column vertex? So this would be the undirected graph version of this, to have just Booleans, is there a connection between these 2 nodes? Each row represents a vertex, each column represents a vertex. So it's true if there's an edge in the graph from the row to the column. And false if no such edge exists. So for this graph, we would get something that looks like this. Graph on the left, adjacency matrix on the right. Is there an edge from A to B? Yes. Is there an edge from C to D? Yes. Is there an edge from D to C? No. So unweighted, as soon as we add weights, we don't make these booleans, we make them integers or doubles, depending on what the legal values are for that. So we just store the actual cost or weight of the edge here instead of just whether there is one or not. So with this, we can ask some interesting questions. Like, how efficient is it to query this structure? So I guess first, questions about the representation here, how this graph is represented by this adjacency matrix? No questions? All right, how efficient is it? How long does it take to get a vertex's out edges? In fact, I'm just gonna go back to it. The question I asked you is, what are all of C's out edges? B and D. Imagine writing a program to do that for an arbitrary vertex. How long would that take compared to something that we could say is a part of this graph? We'd have to query every possible out edge in the C row. So you would say for row C, which values are true, or how many values are true? You have to look at every single column in row C. How many columns are there in row C? The number of vertices. So in general, to figure out what are the out edges to a vertex, it's going to be based on the size of the number of vertices, the cardinality of that set. So big O of the size of the cardinality of V. How about getting a vertex's in edges? So if we look back at this, I want to say, what are all of C's in edges? How long does it take to answer that? Yeah.
Query the column.
Query the columns. So column C now is going to be all of the in edges for C. Is there an edge from A to C? That is row 1, column 3, and everything in column 3 is going to be counting and going over that. So just like with the out edges, it is linear with respect to the cardinality of your vertices. How long does it take to decide if a particular edge exists? If I want to query, is there an edge from B to D? How long does that take? Yeah, it is just constant. It's a lookup in an array. We know arrays don't require any searching as long as you know the row and you know the column. It is constant time to access what the value that's in that cell. How about inserting an edge into the graph? So you're not inserting a vertex, you're inserting an edge between two existing vertices. Thoughts, guesses? It's okay to be wrong.
Linear, because you have to move all the way and see that can insert it.
It actually is just an update in the array. So that's a good guess, but it's actually constant. You're going to take a value that was false and turn it to true. Once you turn it to true, we've represented that an edge exists between those. How about deleting an edge? Same thing, you're going to take an edge that was true and turn it to false. The last really important consideration is how much memory does it require? How large is this adjacency matrix? Does it depend on the number of vertices or edges?
Well, vertices, whatever.
Vertices squared, yeah. There are vertices number of rows, vertices number of columns, so regardless of the number of edges in the graph. The space requirement is always quadratic with respect to the number of vertices in the graph. So now the question I would ask is this structure better for sparse or dense graphs? The answer is, it doesn't matter. It's the same regardless of the structure of the graph. It will always be that V squared space. And all of these things are always constant. They don't change, I should say. I shouldn't use the word constant. They do not change based on the number of edges in the graph. So it's only structured on the number of vertices. And we see that show up because there's no E anywhere in any of these runtimes or space requirements. It's all V. On the other hand, we could use an adjacency list. An adjacency list is not a 2D array, it is an array of linked lists. Each of the heads of these linked lists are going to be where you start for a particular vertex. And then each linked list is only going to contain another node in that linked list if there is an edge between that vertex and another vertex. So now we have a variable length to each one of these lists. So if a list is empty, that particular vertex has no outgoing connections and has no neighbors. So how many elements? What's the maximum size of one of these linked lists?
Size of the vertices.
Yeah, the number of vertices. So here is a graph. Go ahead and I guess we're kind of out of time. So I'm going to show you the adjacency matrix, which looks like this, and the adjacency list, which looks like this. So the adjacency list is just linked lists representing all of the outgoing edges to each vertex. So there are outgoing edges from vertex 1 to vertex 2 and vertex 5. Because 3 is not in that list, there is no connection between 1 and 3. Questions on the concept of an adjacency list? With the last minute of class, let's talk about runtimes of an adjacency list. So how long does it take to get a vertex's out edges? Now think of the difference between dense graphs and sparse graphs, because now it matters. In a dense graph, it's still going to be linear. We'll have to query possibly every other vertex in the graph, so it's based on the number of vertices. That's the longest that linked list could be. On the other hand, if it's a sparse graph, that means on average, there is a constant number of connections between each vertex or for each vertex. Then it's actually constant to query what are the out edges for a vertex. Because it's sparse, there's only going to be one of them, or two of them, or three of them. It's a constant number. Vertexes in edges, exactly the same. Except for dense graphs, we actually have to go through and search every other linked list to see where does it appear. So for dense graphs, yikes. For sparse graphs, it's the same as it was for the adjacency matrix. Does that make sense as to why that is? If an edge exists, for dense graphs, it's worse. It's linear. But it is constant for sparse graphs. To insert an edge is still constant. to delete an edge. Still constant. So space requirement is the same as it was for an adjacency matrix for dense graphs, but it's actually significantly less for sparse graphs. So we can see this is just better for sparse graphs than the adjacency matrix. So now we can actually state that comparatively, the adjacency list is better for sparse graphs and the adjacency matrix is better for dense graphs. Comparatively. So that's why we care to have both of these objects and use them both to represent graphs, because depending on whether that graph is sparse or dense, there's a different structure that is more efficient for storing that graph. All right, we'll end here. We'll come back tomorrow and do our exam review, take an exam on Friday, and we'll come back to this on Monday.
Oh.